Okay, Chemistry 3101. Last class, we looked at um, section 15.4 last, where we were looking at the number of signals produced by a compound. And today we're going to begin by looking at section 15.5, which deals with chemical shift. Now, it says here that in many NMR solvents, we add 1% of this molecule called TMS as an internal standard. So there are many different types of NMR solvents. And remember, we use deuterated solvents. We replace the hydrogens with deuterium. So instead of chloroform, you would have, let's say, deuterochloroform, CdCl3. Dimethyl sulfoxide is a compound we don't talk about a lot in Chemistry 3101, but this is called dimethyl sulfoxide. So in order to use this as an NMR solvent, you have to remove the hydrogens. So we'll get rid of those and you replace them with deuterium. And we call this DMSO D6, okay, which means there's 6 deuteriums in it like that. Anyhow, these are just some examples of deuterated solvents or NMR solvents that we use. And as I told you, we usually add 1%, or chemical suppliers will add 1% of TMS as an internal standard, right? We need a reference point no matter where we're doing our research in the world, okay? So TMS is that internal standard. And so the frequency of the protons in TMS, the reason why we use TMS as a standard is because the resonating frequency of all of these 12 protons that are in here, which are all chemically equivalent, it's going to be much lower, or it's lower, I should say, not necessarily much lower, but it's lower than the chemical shift of, or the resonating frequency of most protons in organic compounds. So how do we measure a chemical shift? Well, it says here the shift for a proton signal is calculated as a comparison to TMS. Now, I'm not going to ask you to do any calculations using this formula right here, but it would be a good idea to understand this formula, okay? So don't just shrug it off and say, oh, if he's not going to ask it, I don't need to understand it, because it's very important that you have a knowledge of what's going on here. So first thing is the delta, the little Greek letter delta, so that's a lowercase d in the Greek alphabet. This means the chemical shift, so chemical shift. So you're going to see me use that symbol from time to time. But the way that we measure the chemical shift is we say the shift, or the observed shift from the tetramethylsilane in hertz, and then we divide that by the operating frequency of the instrument in hertz. Now remember, the operating frequency of the instrument in hertz is directly related to the magnetic field, because last class we talked about the stronger the magnetic field, the larger the energy gap between the alpha and the beta spin states. Okay, so what does that mean? That means if I have a low field spectrometer, let's say my magnet has a field that's around 1.4 Tesla, what we said was, well, in order to get the protons to come into resonance, when we have a magnetic field strength, B0, which is around 1.41 Tesla, we need to use electromagnetic radiation that has a frequency of around 60 megahertz, right? Okay, 60 megahertz. Whereas if we have a stronger magnet, let's say it's around 7 Tesla, well, in that case, you need to, in order to cause those protons to come into resonance, we need to use a higher energy type of electromagnetic radiation. Since we know that E is equal to H nu, we know that energy is directly proportional to not only the magnetic field, but the frequency. So if we have a stronger magnet, we're going to need a stronger or a higher frequency of electromagnetic radiation. So again, if we use around a 7 Tesla magnet, then we have to excite the sample, or to pulse the sample, or to subject the nuclei to electromagnetic radiation with a frequency of around 300 megahertz. So you see that, let's say you look at the protons in benzene. So if we just draw the molecule of benzene, it's C6H6. Well, I'm not even going to draw the protons in, but you know that there are 1, 2, 3, 4, 5, 6 protons, and they're all chemically equivalent. Okay, we have several axes of rotational symmetry, and we also have reflectional symmetry through the molecule. So all 6 of those protons are identical, and we see that if we run a spectrum, an NMR spectrum of benzene on a 300 megahertz instrument, what we see is that the chemical shift of the protons is around 2,181 hertz from tetramethylsilane. So what we do is we divide that by the operating frequency of the spectrometer, and we get this number, 7.27 times 10 to the negative 6. Okay, well, that's all well and good if you have a 300 megahertz spectrometer. Keep in mind there's 10 to the power 6 hertz in 1 megahertz. Well, what would happen if you had that cheaper instrument, right? That less expensive instrument, that 60 megahertz instrument, right? The one with the weaker magnet. Well, what you would find then is if you ran the NMR spectrum of benzene on that spectrum, is now you get a different chemical shift. Or sorry, you get a different resonating frequency is what I should have said, not chemical shift. But you divide that by the operating frequency of the spectrometer, and what do you get? You get the exact same number that we did with the 300 megahertz instrument. So it says that the resonating frequency is what I should say of the signal is different in different instruments, whether it's a 60 megahertz, a 300 megahertz, a 500 megahertz, whatever, but the shift relative to tetramethylsilane remains constant. And that's the important thing. And that is what allows researchers to be able to communicate with one another wherever they are, if they're in different cities, different states, different countries, different continents, whatever, because no matter what type of spectrometer you use, you're always going to measure the resonating frequency, and then you're going to divide that by the operating frequency of the instrument, and you're going to get a chemical shift, which is, notice, it's a unitless number because we're dividing hertz by hertz. Anyhow, so again, that chemical shift relative to TMS, we use the symbol delta to represent that, and we do that, it's a dimensionless number because the units of hertz cancel out. Again, you can do the same thing here. Hertz cancels out. So normally we give the units of parts per million to the chemical shift because it comes out as 10 to the negative 6. So we call it parts per million, which simply indicates that the signals are reported as a fraction of the operating frequency of the spectrometer. So when we report a chemical shift, if we go back here, you would say that, you'd say, well, 10 to the power of negative 6 equals a part per million. So then you'd say that this is equal to 7.27 parts per million. And if you go back to the previous slide, you'd say the same thing, that this is equal to 7.27 parts per million. So again, we're always going to report our chemical shifts 100% of the time in parts per million. And now you know where that comes from. So most NMR signals for protons show up between 0 and 10. I'm going to cross the 10 off and say they actually show up between 0 and 12 parts per million. So that's a correction that I wanted to make to that slide. Why? Because a carboxylic acid will actually, it's the acidic proton of a carboxylic acid will have a chemical shift of around 12 parts per million. So there we go. So now we know what chemical shift is. We know where it comes from. We know that it's a standard that's measured in reference to tetramethylsilane. We know that most protons are going to resonate at a higher frequency, and therefore they're going to have a positive chemical shift. There we go. So a little bit of history here. It says that early proton, or sorry, I shouldn't keep alluding to proton, but early nuclear magnetic resonance spectrometers, so early NMRs, analyzed samples at a constant energy over a range of magnetic field strengths. So what they did is they held the frequency of electromagnetic radiation constant, and they actually changed the magnetic field, right? They obviously put more power in it or less power in it, and that altered the magnetic field. And so when they had a low field strength that caused the protons to come into resonance, they called that the downfield region. And when they had a high field strength, they called that the upfield region. I'm never going to ask you about upfield and downfield, okay? It says here that shielded protons need a stronger magnetic field in order to be excited at the same energy as deshielded protons, whatever. I'm never going to ask you about this bullet point here. The textbook goes into a little bit of detail about this, okay? So yeah, the textbook goes into a little bit of detail about this, but the only thing that you need to know as a Chemistry 3101 student is about downfield and upfield. That's it. When you're on the far left-hand side of the spectrum, we call that downfield, and then the more right you are, we call that more upfield, okay? It's just a historical term, all right? So there we go. So current NMRs, what we do is that we maintain a constant field strength, and what we do is that we vary the energies, right? We vary the range of frequencies with which we subject the sample to. So shielded protons are going to have a smaller magnetic force acting on them, right? They have more, since they have a greater shielding effect, they just feel less of the electromagnetic, or sorry, since they have a greater shielding force, they feel less of the magnetic field. And so they have smaller energy gaps between them. So therefore, they require lower energy radio waves. Whereas when we're downfield, it requires higher energy radio waves. Why? Because we have a larger energy gap between the alpha and the beta spin states because these protons are deshielded and they feel more of the electromagnetic they feel more of the magnetic field. So somebody asked in the chat, they said, what is the advantage of the higher operating frequency? So this is what I was talking about before I started lecturing this morning. I said, what's the difference between a 60 megahertz instrument, versus a 300 megahertz instrument? So the reason why, and what's the difference between a 300 and an 800? Well, besides being money, right? Because a 60 is going to be like, I'll do like a Yelp review. It's like $1, and then here we put lots of dollar symbols, right? As you get to a higher operating frequency. The difference is every part per million, okay, when you get to a higher operating frequency represents more hertz, right? It represents more hertz or more frequency. And so therefore, basically it's resolution, right? It's resolution. And the way I likened it is this: if you have a 60 megahertz instrument, it's like looking at a black and white TV that's, maybe you got a 10-inch screen or something, the pictures, can you see what's going on in a movie in a black and white TV that's really old and small? Yeah, absolutely. But it's not going to be as clear as if you were to watch the movie on a high definition TV that's, a big screen TV. So that's the whole advantage to having a higher operating frequency, is that you get better resolution of your spectrum and you can see the peaks more clearly. So going back here, again, you need to know the terms downfield and upfield, and you need to understand that downfield or deshielded protons require higher energy in order to come into resonance, and that upfield protons are more shielded, and so it requires less energy to get them to come into resonance. So by resolution, I don't mean the spikes. What I mean by resolution is the distance between the peaks in a signal. So this is something that we're going to see later on today. Okay, I promise that we will look at that. Okay, all right, there we go. So what about the chemical shift? Well, there's some general knowledge that you need to have about chemical shift. For example, alkane protons, if you look at any kind of alkane, the protons in an alkane are generally going to have chemical shifts that are around 1 to 2 parts per million. But what happens is that the protons can be shifted downfield, right, to a higher energy portion of the spectrum when we have nearby electronegative atoms. Why? Because they cause deshielding, because they are electron withdrawing. If you look at methane, you look at the chemical shift of the 3 protons, they're all chemically equivalent, and they have a chemical shift of 1 part per million. But what happens as we put a halogen, whether it's iodine, bromine, chlorine, or fluorine, you see that the chemical shift increases. Why? Because these are electronegative elements and they have an electron withdrawing effect, but you see that it gets bigger and bigger and bigger as we get all the way up to fluorine, which is the most electronegative element. So this is an inductive effect, essentially, right? So if the fluorine is the most electronegative element in the periodic table, it's going to be sucking a lot of electron density away from these protons. What's the net effect? If they have less protons, less electron density circling around the nuclei, right, because it's being sucked away by that electronegative fluorine, then you have less of that opposing magnetic field, okay? And therefore, they're going to feel more of the net magnetic field, and therefore there's going to be a greater energy gap between their alpha and the beta spin states. Therefore, it requires a higher frequency of electromagnetic radiation to get them to come into resonance. Therefore, they have a higher chemical shift. So the more electronegative an atom is, the greater inductive effect it has of electron withdrawing, the higher the chemical shift is going to be. And you can see that that effect is additive here. If you go from chloromethane to dichloromethane to chloroform, right, from here to here to here, you see that what's the effect of adding more and more chlorines, right? The chlorines are electron withdrawing. So if we have one, well, that's got some deshielding effect compared to methane. But if you add two, then you've got 2 electron withdrawing groups. Then you get 3, right? What happens? what happens is that the protons that are left over are more and more deshielded. And the more deshielded a proton becomes, or more deshielded it is, the greater the chemical shift will be. If we take a look at this compound here, so this is 1-chloropropane, you notice that on the alpha carbons, the effect is the most pronounced, right? Look at the chemical shift here. Okay, you can see the chemical shift is around 3.3 parts per million. If we go to these beta protons here, think about it. The electron withdrawing effect of that chlorine isn't going to be felt nearly as much by the protons on a beta carbon. Why? Because they're further away. And I can tell you right now that the effect on gamma carbons is basically negligible. Okay, it feels basically nothing of that chlorine because it's too far away. So it's not only the type of element, that's what we're seeing right here. It's not only the number of whatever element we're talking about, it's also the proximity, right? So now we've got three different effects that, or three different, sort of things that can affect the chemical shift of a proton. So a baseline that you're going to want to have for chemical shifts with respect to TMS, okay, is a methyl, a methylene, and a methine. Okay, everybody has to have this, memorized. Just put it in your hat, kind of thing. If you have a methyl, a CH3, right? All three protons are chemically equivalent, and they're going to have a chemical shift baseline of 0.9 parts per million. Okay. Now, of course, if you add electron withdrawing group, that's going to affect it, but we'll talk about that more later. Next is if you have a methylene, the baseline for a methylene is going to be 1.2 parts per million. And the baseline for a methine, the proton of a methine, is 1.7 parts per million. So these are just baselines that everybody has to be aware of. And then what we're going to do is we're going to use table 15.1 to help us adjust the chemical shifts depending on the proximity to certain functional groups. And the functional groups that we're going to look at will be an alcohol, an ester, or a ketone or aldehyde. I'm going to show you that right here. So table 15.1, you will not have this table on your quiz, so will not have this table for quiz or exam. So it'd be best to familiarize yourself with this table. And of course, we're going to look at some practice problems where we use the table. And there's some practice problems in the textbook where you have to apply this. So here's what happens. If you have your methylene, okay, what was the baseline of a methylene, a CH2? Well, we just looked at this on the last slide. We said the baseline is 1.2 parts per million. If that methylene is right next to an oxygen of an alcohol, what you do is you add 2.5 parts per million. Why would that be? Because oxygen is the second most electron withdrawing group in the periodic table, and it's going to pull electron density away from these protons. I'm going to repeat myself for like the sixth time now. What happens if you remove electron density away from the nuclei, right? Then they're going to be deshielded. They're going to feel more of the net magnetic field. That's going to cause a greater energy gap between the alpha and the beta spin states. Therefore, you need a higher frequency of electromagnetic radiation for the protons to come into resonance. Therefore, they have a higher chemical shift. So it's the same, concept every time. So that electron withdrawing group, that oxygen of an alcohol, we had 2.5 parts per million. And so the estimated chemical shift that we get is 1.2 plus 2.5, so 3.7. And you can see that the actual chemical shift, look at this, bang on the money. It's 3.7 exactly. Now, if your two protons are next to the oxygen of an ester, in that case, you actually add 3 parts per million, okay? And you can probably guess that not only do you have the electron withdrawing effect of the oxygen, right, but you know that you could also draw a resonance structure, right, where you move this over here to show that this is, partially electropositive, which is going to suck even more electron density away. And that's why the chemical shift is so greatly affected. You add 3 parts per million. So let's say you had this molecule here. This is ethyl acetate. Look at the two methylene protons. What's the baseline? 1.2. They're right next to the oxygen of the ester. We add 3. We get 4.2 as our estimate. And the actual chemical shift is 4.1. Okay. I'm going to talk about this thing in a second here, but I want to move on. Okay. The next one is if your methylene protons are next to the carbonyl of a ketone or an aldehyde or an ester or an amide, whatever, is that generally speaking, you add 1 part per million. So you have this molecule here. This is called 3 pentanones, neither here nor there. but since the two protons are right next to the carbonyl carbon, you add 1 part per million. The estimate is 2.2. The actual chemical shift is 2.4. It's pretty darn close. So those are the three effects of neighboring functional groups on chemical shifts that are covered in this table. You can go look around the internet. You can look at other handbooks and tables that are found on, the internet maybe, or you could buy another textbook. But another good resource would be the Schafstall textbook. I don't know if you're using that, Schafstall textbook that's used in Chemistry 3102, sometimes in Chemistry 3112. That has a more exhaustive table of chemical shifts that could be useful for you. So I want to get back to this part here and talk to you about this bullet point here. It says the effect of beta protons, or the effect on beta protons rather, is 1/5 the effect of alpha protons. Let me show you what I mean. Okay, this is ethanol. Okay, this is the alpha carbon, and this is the beta carbon. So that means that these are the alpha protons, and the 3 protons here, 1, 2, 3, these are beta protons, right? Now, what did that bullet point say? It says the effect on beta protons is about 1/5 the effect on alpha protons. So can anybody tell me what the baseline was for the 3 protons of a methyl? You go back to the previous slide. Could anybody tell me what the baseline chemical shift for the 3 protons of a CH3 of a methyl group? Exactly. It's 0.9 parts per million. Okay. Now it says it's 1/5, right? 1/5. If the effect is plus 2.5, what's 1/5 of 2.5? It's 0.5. So we would add 0.5 parts per million. That would give us a chemical shift of 1.4 parts per million for these 3 protons. Now keep in mind, this is just an estimate, but that would probably be a very good estimate. And we're going to use this all the time to estimate chemical shifts of protons. In fact, I think I have a question. Yeah, I have a question here where we're going to actually try that out later on this morning. Okay, so again, you won't be given this table. I recommend that you familiarize yourself with it so that you are able to apply that. Well, what other things can affect chemical shift? I mean, what have we looked at so far? What could affect our chemical shift? We said the type of atom that's next to a proton, the number of atoms, okay, the proximity, functional groups, whether it's an alcohol, an ester, or a carbonyl containing functional group like an aldehyde, ketone, amide, ester, whatever, okay? Well, here's another factor that can affect a chemical shift, and it's called an anisotropic effect, or anisotropic effect, however you want to say it. Now, if you read the opener here for this chapter, it talks about anisotropy a little bit, but let's take a look and see what it is. It says that when the electrons in a pi system, okay, are subjected to an external magnetic field, they circulate and make a magnetic field, causing diamagnetic anisotropy. And all that diamagnetic anisotropy means is that different parts of a molecule basically have different, magnetic field strengths acting on them. Okay, so let me draw the structure of benzene, which is this right here, and everybody knows the structure of benzene. It's C6H6. So you have 3 sets of pi electrons, and sometimes we draw benzene like this, where we just put a circle inside, right? Because all those electrons are conjugated in the system. But anyhow, here's our benzene molecule. So what happens is, when you subject benzene, and this is supposed to be benzene in here, okay? They don't show you the pi electrons because they're represented by the blue circles here. And I'll talk about that more in just a second. Okay, but you take a benzene molecule, you put it in an NMR spectrometer, you subject it to a strong magnetic field. What does that cause? It causes the pi electrons in the molecule to start circulating around and around. And that's what's represented by this darker blue arrow here. You see how there's the circulating pi electrons right here. Okay, so it basically causes a little electric current. So when you have an electric current, what's that going to do? It's going to create a little magnetic field. So here are the field lines. Now notice carefully, follow the field lines. I'm going to use a red pen. Notice that they're going down in the inside of the ring, okay? But they're going up on the outside of the ring. Ooh, that's kind of interesting. So what that means is that the inside of the ring, okay, is going to be more shielded. Why? Because it's got the little induced magnetic field that's acting against the applied magnetic field, whereas the protons on the outside of the ring, which are the only protons, there's just 6 protons and they're all outside the ring. That means they're all going to be extra deshielded. Okay? They're going to be strongly deshielded. Why? Because again of that little electric current caused by the circulating pi electrons, which causes that induced magnetic field. And again, since the protons are on the outside of the ring, they have the additive effect of this new magnetic field. Okay, so the whole point of diamagnetic anisotropy is just that on the outside of the ring we have an extra magnetic field, so a deshielding effect. Whereas the inside of the ring, and there aren't any protons there, but that is more shielded. Okay, so 2 parts of the molecule have 2 different sort of magnetic fields or magnetic environments. So this is what I was just saying. The diamagnetic anisotropy means different parts of the molecule have different magnetic field strengths. So again, this is just rehashing what I said, is that the regions outside the ring, which is where the protons are, have an increased magnetic field. I'm going to repeat myself for the 7th time, okay? We have a greater magnetic field. What does that mean? We have a bigger distance or difference between the alpha and the beta spin states. What does that mean? We need to hit it with a higher frequency or higher energy of electromagnetic radiation to cause those protons to come into resonance. Therefore, they have a higher chemical shift. So basically, the protons on a benzene ring are going to have a higher chemical shift than what you might expect because of diamagnetic anisotropy. If we look at the proton NMR spectrum of ethyl benzene, and that's this molecule here, you've got an ethyl on your benzene, so this is ethyl benzene. You see these 5 protons, okay, that are highlighted here in red, and yes, I know there's 5 more protons here, but the 5 that are highlighted in red, those are what you call your aromatic protons. Notice that they all have a chemical shift of what? If we zoom in here, it tells you, like point blank, these are the aromatic protons. You have 7.1, 7.2, 7.3. So let's say they're around 7.2 parts per million, okay? Or you could say they're in between 7.1, to 7.3 parts per million. That's the chemical shift for those protons. Well, the reason why their chemical shift is so high, the reason why they're so far downfield, is because of that effect of diamagnetic anisotropy. All right, so aromatic protons are always going to show up in the neighborhood of around 7 parts per million. Okay, notice it says neighborhood. It doesn't say exactly 7 parts per million. It's around 7 parts per million. There's one more thing I want to point out to you here. Check this out. You know that there's a methylene here, right? A CH2. Okay, well, I'm just going to tell you point blank, and we're going to learn how to figure this out later on. But you can see that the chemical shift of the methylene protons of the CH2 is right around 2.6. Okay, so they come at around 2.6 parts per million. If you go back in your slides to maybe 4 or 5 slides ago, I told you that the baseline for a methylene was 1.2 parts per million. Why would the chemical shift be higher than you expect, right? You can see it's shifted by an extra like 1.3 parts per million or something. That's because the methylene protons experience some of that increased magnetic field as well, right? Because they're so close to the ring. Whereas when you look at the methyl protons, the CH3, okay, so I'll write those, maybe I'll write them in black, okay? The CH3, okay, the methyl protons, we said that the baseline for a methyl was 0.9. Now you see that the chemical shift of the methyl, okay, so these are this is the CH3 right here. This is the CH2, okay? You can see the chemical shift of the CH3 is around what? 1.2 maybe? Something like that. It's around 1.2 parts per million. Well, is it deshielded compared to the baseline of the methyl, which is 0.9? Yeah, but not as much. Why? Because it's further away from the aromatic ring, okay? So you can see that you've got to take a lot of things into account when you're looking at an NMR spectrum. Now, the whole concept of, there being 4 peaks in this signal and there being 3 peaks in this signal, we're going to talk about that in a couple of sections. So don't stress about that yet. We'll get into that in detail. So this is essentially the table. I don't give you this table on the handout, but it's essentially this table summarized in the handout that you're allowed to bring into your quiz is pretty close to this, okay? So table 15.2. So don't come at me and say, Mr. Dion, you said you'd give me table 15.2. No, I said I'd give you the handout, which is pretty close to table 15.2. So you want to compare the two. But it's a good idea to familiarize with these chemical shifts values for common types of protons that come up, every day when you're an organic chemist. So let's take a look. Right, we already looked at a methyl, a methylene, and a methine. They have chemical shifts around 0.9, 1.2, and 1.7 respectively. If you have an allylic proton, right, you know the difference between a vinylic position and an allylic position. So this is a vinylic carbon. This is an allylic carbon. So the allylic carbon, this is the allylic proton. It has a chemical shift of around 2. If we skip ahead to the vinylic proton, it's got a much higher chemical shift, around 4.5 to 6.5 parts per million. We already looked at aromatic protons. We said they're around 7. Here it says 6.5 to 8. Some other ones that I think don't take that long to memorize are an aldehyde is pretty unique. It's around 10 parts per million. And I told you earlier today there was a little typo in my slide. It should have said up to 12 parts per million. And the carboxylic acid proton will come out around there. Other ones that are important are an alkyne. If you have a terminal alkyne, so that means there's a hydrogen on the sp hybridized carbon or one of them, then that's going to have a chemical shift around 2.5 parts per million. Aromatic methyl, right, just like the aromatic methylene that we saw on the previous slide. What was its chemical shift? Let's go back. It was what? 2.6. So if you have an aromatic methyl, attached directly to the aromatic ring, it's around 2.5. What else? An alkyl halide. Well, the halide can vary from an iodine to a chlorine to a bromine, right, to a fluorine. So the chemical shift can vary. Alcohols have a wide range of chemical shifts, 2 to 5. It can even go outside of that. Okay. But again, these are the types of things that show up in molecules that we're going to see all the time in chemistry 3101. You'll see them as well in chemistry 3102, and you'll see them in chemistry 3111 and chemistry 3112. NMR is one of those things you can't get away from when you're an organic chemist. So let's take a look at a question where we have to apply some of this information. So you might want to refer back to the tables, table 15.1 and table 15.2. And it just asks us, it says, for each of the following compounds, identify the expected chemical shift for each type of proton. So think about what we're doing. Let's say you're an organic chemist and you're working in a research institute, and I can tell you that I don't think this molecule has any biological activity. But imagine that what I have in the yellow circle here, you've got an alkyne, you got an alkene, you got an aldehyde in this molecule. Imagine that was some kind of blockbusting drug. Okay. Imagine this was a $1 million seller, and you were going to run the NMR on it for the first time. Now, that's kind of putting the cart before the horse because you'd run the NMR way before you found out that it's a blockbusting drug. But imagine, so if a scientist gave you this structure, you would want to have an idea what the NMR should look like before you run it. Okay, so let's see if we can come up with some estimations of what the different protons' chemical shifts will be. I'm going to start with the aldehyde proton, and this is not a trick question. I hate trick questions. Could anybody tell me approximately what the chemical shift would be of the aldehyde proton? Yeah, it's going to be around 10 parts per million. Exactly. And where did you get that? Right, Mackenzie went right back here, and she said, okay, well, there we go. Proton, aldehyde, yep, around 10 parts per million. Okay, let's move on from there. Here we have a methylene, right? This is just a CH2. Now, we got to be careful about this one, okay, because it's not just a regular old methylene, is it? Could anybody tell me, would these be protons, this CH2, would it be considered allylic or vinylic? And again, I'm not trying to trick you or anything. Sorry, I can't see. So these would be allylic. Okay, so these would be allylic protons. All right. So if we go back, okay, go back here. Okay, we saw that allylic protons, right, have a chemical shift of around 2 parts per million. Okay, So think about it. If you have the double bond here, right? This is the vinylic position. This is the allylic position. So this is an allylic position here. Okay. There we go. All right. So we have an allylic position. So that's going to give us a chemical shift of around 2 parts per million, but it's also right next to the carbonyl of an aldehyde. If we go back to table 15.2, and I'm not going to do this for every proton, but you see, if you're next to the carbonyl of a ketone or an aldehyde, ester, etc., you add 1 part per million. So we take that vinylic 2 parts per million, and then we add 1 part per million to it, and we end up with 3 parts per million. Okay, there you go. So we have, again, allylic protons plus 1 part per million. All right, let's take a look at the next one. We have a proton here. I'll use a green pen. So this one is a vinylic proton. So vinylic protons, vinylic proton has a chemical shift of what? Around 4.5 to 6.5. Okay, so around 4.5 to 6.5 parts per million. Now, there's one thing I noticed, and I actually looked at the solutions manual for this one, and he writes that it's around 4.5 to 6.5. And there's nothing wrong with that. Okay, but if you look at the carbonyl here, this is the alpha carbon, this is the beta carbon. So technically this is a beta proton. So you would add 1/5 of 1 part per million, so 0.2. But I think the reason he didn't write 4.7 to 6.7 is because the effect is so small that, you know, it's not really great enough to change it that much. So I think that's probably why he left it out. But if we look at this proton here, I mean, again, this is just your everyday vinylic proton. So we'll put here vinylic. So again, it's going to have a chemical shift of around 4.5 to 6.5 parts per million. Let's do the next one. Could anybody tell me what types of protons are in this methylene that I have in the red circle here? And again, I'm not trying to throw you for a loop or anything. I'm just want to make sure we got this down a little bit. Yeah, excellent, Allison. They're allylic. Yep, absolutely. So these are just plain old allylic protons. There's no extra electron withdrawing effect here. So allylic protons have a chemical shift of around 2 parts per million. The next one is just a straight ahead methylene. Okay, so a methylene has a baseline of around 1.2 parts per million. There's no extra electron withdrawing effect there. And then the last one is the terminal alkyne. And the terminal alkyne, again, if we go back to our table, and again, don't want to do this every time, but the terminal alkyne proton has a chemical shift of around 2.5. So let's go back here. We'll say that this is around 2.5 parts per million. So there you go. Now we have an idea of what the chemical shift of all of our protons are, you know, roughly. I'm going to do the next one a little bit quicker. The first thing I noticed right away is that we've got 2 vinylic protons here. Okay, both of these guys are vinylic. So they're going to have that chemical shift of around 4.5 to 6.5 parts per million. All right, that would mean that these protons here are allylic. So we have allylic. So they're going to have a chemical shift of around 2 parts per million. What else? We have allylic protons here. Okay, so these are allylic. However, so we'll put here allylic, which means around 2 parts per million. But if we have an alcohol right here, right, this is an alpha carbon and this is a beta carbon. So we add 1/5 of the effect of the alcohol, and the alcohol increases the chemical shift by 2.5 parts per million. So what's 1/5 of 2.5? We add plus beta, we'll put here beta to OH. So we're going to add 0.5, so that gives us 2.5 parts per million. Then we have the alpha protons. So for the alpha protons here, we have the baseline of a methylene, which is 1.2 parts per million. I'll leave the units out. Plus, we have 2.5 that we want to add to that. So that's going to give us 3.7 parts per million. And then we have the alcohol last. I'll use the green pen for that. And we said that an alcohol has a chemical shift. Go back to the table here. It's in the neighborhood of 2 to 5 parts per million. So let me scribble that down here. So 225 parts per million. And there you go. All right, what do you think? Give me a thumbs up if you follow me. All right, cool. Is it something that you're going to master in, the first time you try it? Maybe not. Maybe not. But it's one of those things, if you look at it enough, you get a little bit of practice in it, you'll start to get the hang of it and start to know what to look for, right, with in terms of your chemical shift. So if we just kind of review what we've talked about this morning, is that we looked at all the different types of chemical shifts. Again, you're going to be given something similar to this table, again, which is on the handout. It's the first thing I posted in the chat this morning. So you can take a look at that. On our table, it says typical values of proton NMR chemical shifts, and then below it, there's carbon-13. And we'll talk about that later this morning. But yeah, so you should familiarize yourself with these. Why? Because they come up so much. You don't want to depend on a handout for everything that gets annoying. But table 15.1, I will not give you that. Okay. And when I was an undergraduate student, I never even saw this table. It wasn't in any textbook that I, studied from. But it does do a great job at approximating chemical shifts. So super duper handy. Anyhow, kind of cool. All right. I thought you might enjoy the section on chemical shifts. And then the whole idea behind anisotropic effects, diamagnetic anisotropy. Our book goes into a little more detail about diamagnetic anisotropy, and I'll just throw this out there. It's not in my slides. I'm not going to ask you about it directly, but there's a really cool example, and it's called 14-annuline. And if you look at the magnetic field that's caused, or that's produced by the induced magnetic field in 14-annuline, you have protons on the outside of the ring, and then you have protons on the inside of the ring. And check this out. The protons on the inside of the ring are so shielded that they actually have a chemical shift that's lower than TMS. They have a chemical shift of -1. Now, I am never going to ask you about anything with a chemical shift of less than 0, but I just want you to know that it can exist. Okay, so you want to be sure to take a look at that specific example. It's pretty cool. It's pretty cool. Out of all the thousands of NMR spectra that I've run in my life, I've maybe run, 2 things in my life where I had a chemical shift that was less than 0. Okay, didn't come up a whole lot. So, but it can happen. Anyhow, so after chemical shift, next thing I want to look at is integration. Integration is a little faster than chemical shift. There's a little less concepts to look at here, but the idea is this. It says the integration, or the area under a peak, quantifies, notice this word, the relative, okay, the relative number of protons giving rise to a signal. So a computer, so you don't have to do this, a computer is going to calculate the area of each peak representing that area with a step curve. When it calculates the area, there is no units. It's not millimeters squared, it's not centimeters squared, it's not feet squared, it's no units. But take a look at this spectrum here. You've got 4 signals, right? You've got this signal here, you've got this one here, you got this one here, and then you've got this one here. Okay, so you've got a total of 4 signals. Now, if there's somebody in the class who's really splitting hairs, and you're like, what is that? You're like, I don't know. It might be an eyelash, or something. I don't know, but it's just something very small that can be ignored, okay? But what the computer literally does, you'll have to bear with me, you guys here. I'm going to zoom in really far. Son of a gun. Not that far. But what the computer does is it actually measures the area underneath the signal, okay? So what I'm shading in green here, it will measure that, okay? Exactly, and then it gives you a relative area. So it says, okay, the relative area of this is 27, and then it will measure the relative area under the next signal, okay? So it measures this area, and I'm not going to do this for all the signals, okay? But it'll measure all that, and it'll say, well, that's got a relative area of 40.2. Well, what's a bigger number? 40.2. So again, it tells you the relative area. But what's cool is that the relative area is proportional to the number of protons. Cool, huh? So you can see that even though the numbers aren't exact, I mean, this one's 27 and that one's 28.4. So that means that those 2 signals are representing the same numbers of protons, right? You see here you've got 40.2 and 42.2. It's close enough that these 2 are representing the same number of protons. Now, there's something else here called a step curve, which are these things here, and what you literally do is you take a ruler, okay? You take a ruler and you actually put it on the step curve, okay, like this, and you would measure the distance between the bottom of the step curve and the top of the step curve. So you would measure this height, okay, in millimeters, and then you would do the same thing for this one here, okay, and you do it for all of them. You'd measure the height from here to here, okay? So you'd measure the height here, you'd measure the height here. But again, it's done for us. You know, they give us the relative height. So if you didn't have these numbers down here, you could actually measure the difference or the distance between the top and the bottom of the step curve, and that would give you the relative numbers of protons. Okay? Now, if you want to know what I mean by relative number of protons, if you don't follow me on that, let me show you some more detail on that. So, if we set the lowest value of these integration values on the very bottom of the page, if we set the lowest number, which is 27, if we give that the number 1, okay, how did I get that number? I took 27.0 and I divided it by 27.0, and what do I get is 1. Well, if I take 28.4 and I divide it by 27.0, I get 1.05. So you can see pretty clearly that the ratio here is close enough. They're never going to be exact. It's just close that it's a 1-to-1 ratio. Now, if you take 40.2 and you divide that by 27, you get 1.48, okay? If you take 42.2 and you divide it by 27, you get 1.56. So you can see the ratio here is 1-to-1, but it's, 1.5 to 1.5. But look, if you were to just look at these numbers that I have the highlighter on, you would think, okay, well, this represents 1 proton, this represents 1.5 protons, this represents 1 proton, and again, this represents 1.5 protons. Well, my friend, there is no such thing as 1.5 protons, is there, right? In a molecule. You can't be like, well, I've got 1.5 protons. No, you've either got 1, 2, 3, 4, right? You've got to have some kind of integer. So what would you do to change all these numbers to whole numbers? Can anybody tell me? What's the easiest thing I could do to manipulate all of these numbers at the same time and change them all to a whole number? I'd multiply them by what? What would you want to do? You'd multiply them all by, exactly, you'd multiply them all by 2. What happens if you took every number in here and you just multiplied it by 2 in your head? Then you end up with something that looks more reasonable. This looks like it represents 2 protons, 3 protons, 2 protons, and 3 protons. Now, if you're really trying to split hairs and say, Mr. Dion, excuse me, but 2.96 is not 3. Mr. Dion, 3.12 is not the same thing as 3. I never said it was going to be exact, okay? It's close. It's very close. Now, if you want to hear something funny that I didn't even know until after I got into graduate school, like nobody had ever told me this, but when I first started working in industry, I worked with a guy who was, 30 years older than me. I shared an office with this guy, and he told me, he's like, oh, for the integration, he said, you know what, man, when the NMRs first came out in the early 70s, he said we would print the spectra on heavy stock paper. So he said, the printers weren't that great, but he said we had printers and we print them out on heavy stock paper. And he said, I'm not kidding you, man. We would literally take a pair of scissors and we would cut the peaks out and we would weigh them on a balance. You'd weigh the paper, physically weigh it. And you'd say, okay, well, this weighs 2 grams, which is impossible, but you get my drift, okay? And then you'd cut this peak out like that, and you'd say the weight is around 3 grams. Again, that's way too much. Let's say it's 0.2 grams to 0.3. And he said, that is how we figured out the integration. And I was like, this is why I'm glad I wasn't alive then, okay? That would have been hell. And he's like, well, it wasn't easy, but that's what we did. Okay, give me a thumbs up on you just follow me on the step curve and the integration values, meaning the relative numbers of protons. Relative. Okay. Now, Allison and everybody else, let me take it one step further. Okay. It doesn't necessarily mean that this is exactly 2 protons, this is 3 protons, this is 2 protons. It means the relative numbers of protons are 2 to 3 and 2 to 3. Okay. This could just as well be 4. This could just as well be 4 protons, 6 protons, 4 protons, and 6 protons, right? If you doubled all of those numbers, okay, so again, it's just the relative number. And then if you're like, well, then how the hell do I know? Well, you'd have to have more information. You'd have to maybe have a molecular formula or something. Now, here's a question that would also be kind of obvious. Um, if you might be saying, Mr. Dion, why would you put the step curve on the spectrum if you've already given me the integration values? That's like wearing a belt and suspenders at the same time. Well, it's a textbook, okay? It's a first year organic chemistry textbook. So just trying to show you multiple things on the same slide. Okay, there you go. Now look, I'll be honest with you that normally on an NMR spectrum in 2021, like if you were worked as a researcher, let's say at UCCS, what you would do is you would set the integration area, like you'd select an area, you'd say, I want to integrate from here to here. It would show you the step curve, but then it would give you the number below it. Okay. And then you could even set this number to 1 yourself. Okay. With a computer. All right. There you go. Anyhow, so what I was saying is the integrations are just relative. Okay. That's a very important word. Relative quantities rather than an absolute count of protons. Because let's say you had this molecule here, right? You've got an axis of rotational symmetry. So you know that these 4 protons that I have in red, they're all chemically equivalent. And these 6 protons that I'm highlighting in blue, those are all chemically equivalent. So you'd see 2 signals, right? Again, because these 2 are identical and these 2 are identical. So you only see 2 signals, but the relative integrations would be 2 to 3. It wouldn't be 4 to 6. So you would have to know more information to say, okay, well, it's not 2 protons and 3 protons. It's actually 4 and 6. All right. So this is what you might see on your spectrum. Let's say you ran a spectrum on this compound and you checked the integration. Well, if you take 32.5 and you divide it by 32.5, you get 1.0. So now we've got 1.0 here. If you take this and divide it by 32.5, I already did the math, you get 1.48. Okay, so that's around 1.5. There's no such thing as 1.5 protons. So let's multiply everything by 2. Then you'd have 2.0 and 3.0. So maybe there's 2 protons and 3 protons represented by each signal, but you know that there's actually 4 of the methylenes and there's 6 for the methyl. So it actually represents 4 and 6. Okay, so I should have just put 4. So again, it's just relative numbers of protons. It's like putting a puzzle together, all right? So if you knew the molecular formula was C5H10O, then you know you've got 10 protons, so then 4 plus 6 makes sense. All right, so with all that spinach in mind, let's take a look at a problem. And this comes straight out of your textbook, okay? And these require a little bit of math. If you don't have a calculator, you can just use your cell phone for now, for a lecture. You can't bring a cell phone into an exam or anything like that, but you could just give it the old college try now. Let's see here, 15.11. It says you got a compound. Here's the molecular formula, C5H10O2. It's got the following NMR spectrum. Determine the number of protons giving rise to each signal. So we've got 4 signals in the compound. We know we've got a total of 10 protons. What's the smallest number here is 33.2. If I divide this by 33.2, then I get 1. If I divide this by 33.2, I get close enough to 1. If you divide 48.4 by 33.2, what you get is around 1.5. So we'll put 1.5 here, and the same thing, right? You get around 1.5. Let me make that a little neater. So 1.5 and 1.5. So again, the relative number of protons represented here, 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 and here is 1, 1.5, 1, and 1.5. I have a question for you. Okay, I'm just going to throw it out there and see if anybody can solve it. You see this signal at 2 parts per million that I'm putting in the blue box? Could anybody tell me quickly how many actual protons are represented by this signal? Could anybody do the mental math? Just do it in their head. Like, does this represent? Yeah, exactly. It must represent 3. Exactly. Kelly, Mackenzie, Allison, you're all correct. How did they know that? Right? How did they get that so quickly? Because they said, well, look, if I add 1, 1.5, and 1 and 1.5, what do I get? I get 5. 5 is half of 10. So if I multiply everything here by 2, then it tells me that this must represent 2 protons, this must represent 3, this must represent 2, and this must represent 3. That is it. If you understood that, you, my friend, understand integration, okay? The problems are not going to get much more difficult than that with respect to just integration. I'll throw this one out. Look, I'm going to be totally frank with you. Look, I just wanted to answer this one a little quicker. Here we have 10 protons again. So we have a total of 10 protons. Here are the relative heights, 17.1, 18.7 to 51.1, and then you got 87.1. So the smallest number here is 17.1, but I want to tell you that I've done this one, okay? I've done the math here, and the 18.7 and the 17.1, they both represent 1 proton. And you're like, well, that's not very close. 18.7 and 17.1, come on, Mr. Dion, those are kind of off. That's a little squirrely. Well, is it? Because you look at the poor person, the poor individual that tried to select the area for this signal here, and maybe they took a little bit of this part too, by accident or something. So again, they're just approximate values. You're going to have to put your thinking cap on a little bit, which I know you're all capable of doing. So if we take 17.1, we divide it by 17.1, we get 1. If you take 87.1, divide it by 17.1, you get around 5-ish. Divide this by 7, the son of a gun, 17.1 again, and I'm really approximating here, but you get around 1-ish. And if you do it here, 17.1, you get around 3-ish. So then you have 1, 5, 1, and 3. Well, this one, you can see that 1 plus 5 is 6, plus 1 is 7, plus 3 is 10. So this must represent 1 proton, 5 protons, 1 proton, and 3 protons. And that's how you use integration. Again, the values aren't always going to be given to you on a silver platter. Like, here you go, it's going to work out perfectly every time. But you know what? I know you're all capable of figuring these out. So that's what integration is. Yeah. Anyhow, so now what have we learned this morning? We've talked about chemical shift. If I had 10 seconds to teach you about chemical shift, I'd just say the more electron withdrawing groups you have, the higher the chemical shift, okay? Essentially, So the more deshielded the proton is, the higher the chemical shift. Then we looked at integration, which again is given to you by a computer. So you just have to learn how to use it, and it just indicates the relative number of protons for each signal in the spectrum. And next, we're going to take a break right now, but the next thing that we're going to talk about is probably the most key out of chemical shift, integration, and multiplicity. I'd say multiplicity is the most key, because if you remember, the first thing I told you in this chapter, and I mean, if you go all the way back to 15.1, I said that NMR can help you determine the connectivity of a molecule. Well, we haven't touched that yet, have we? We haven't touched, like, is the methylene connected to the methyl? Is a methyl connected to a methine? So on and so forth. And that will be explained in section 15.7 when we cover multiplicity, right? Because we've seen all kinds of signals, but we didn't really look at, like, why are some signals 3 peaks and produce a triplet? Why are some signals 4 peaks? Why do some produce a quartet? Why do some of them have 7 peaks? Why are some of them what's called a septet? And that's what we're going to answer in the next section.